Welcome again to the Southwest Climate Podcast. Mike Crimmins, how you doing?
Hey Zach, happy holidays. We're almost there. Some
Boy,
well-earned
that
time
was
off.
an exciting you had an exciting tone to your voice.
I know.
Are you
We're at the
looking
cusp.
forward to it, or is this a time that brings you mixed feelings?
Oh no, I'm a fan. I'm a
Yeah.
fan. I'm a fan of not working, not checking email for just a brief amount of time. That'll be great. And I know you're going to travel too, right? You guys are taking off next week.
Yep. No, I this is a great time. I things quiet down a little bit, the freneticism. I tend to get to concentrate on things that I want to do more. So yeah, I'm I'm
Yeah,
I'm happy. I'm happy.
100%.
Okay. So I'm excited for this podcast because we're doing something that we haven't done before, and it's really the idea of our new producer, Stacy. So kudos to her. And that is we solicited for people that, follow us, follow this podcast for questions, any kinds of questions about the weather and climate of the Southwest. And we would attempt to answer them. I can't promise that we're going to provide definitive answers because some of the questions are really good and they really push the limits of what the science knows at the moment or can say at the moment. So I'm really happy and excited about this. We're going to try to cover a number of these. Not sure how many we're going to get through. Unsurprisingly, and to much of my delight, the majority of them are about the monsoon. So, Mike, the middle of the winter, we get to talk again about the monsoon. So, how fantastic!
We get to do it in December.
Maybe we should just we should rename the podcast to the North American Monsoon Podcast. How about that?
That's probably right. And we often end up talking about Tucson too. So we're always apologizing to the people outside of the rest of the Southwest. We've got to broaden it out a little bit. But yeah, like every month we could just do like a recap of our favorite monsoon. It's like one of those podcasts on old TV shows. They just recount, episode 49. That could be us with the monsoon.
Well, we won't get there in this month's or in this podcast, but I do want to note that if we weren't doing this, we would probably be talking about El Nino, which is the thing that we talk about. This maybe the second most common topic of our podcast after the monsoon is El Nino, and I just do want to note that it's increasing in strength and it's showing more and more signs that we're going to have a strong El Nino event that will rival some of the strongest on record. So that's kind of exciting news. I think there. I don't think we would have expected this, 4 months ago that we'd be maybe cresting the strong category. But there we are. So I'm just going to leave it at that. But that's maybe the news, the climate news, at least for us for the winter. It has a particular form. It's an east-based El Nino, so that's a little bit different than the 2015, 2016 more central-based El Nino. So we'll talk about that next month, though. But I'm
Yeah,
just
it's
gonna.
it's got promise, and I think if we revisit that and we'll pull up, we got a paper we're going to go over that kind of talks about this and the preset patterns across the West next month, but we should be in fully engaged in prime time El Nino next month, and then we can revisit where we've been and then where we may end up in the January, February, March period, which would be the action.
Fantastic. Okay. So I've ordered these questions in in logical order in my brain, which will probably come out pretty muddled. But let's start with a climatology question. So this is a question from Dan, and he writes, we are based in Northeast New Mexico in the I-25 corridor. What is the predominant drivers of summer weather and precipitation? Are we full on monsoonal, more influenced by plain state weather patterns, or somewhere in between? So, awesome question. Let me start though, Mike, because I think this gives us a door into talking about the broader climatology of the region. And then we can talk specifically about Northeast New Mexico. Okay, so whenever there's a climatology of the Southwest kind of question, I always dig up a paper by Paul Shepard and others from 2002 called The Climate of the Southwest. Okay, so I'm going to generalize here, pull out some main characteristics of our regional climate. Okay, so first of all, people, fans of or listeners, I should say, of this podcast probably know all these details.
To be clear.
Okay, so obviously it's a region of low annual precipitation and seasonal warm weather. Okay? Now, obviously there's variability and warm is relative, but compared to other regions. We have two wet seasons, and one of those is monsoonal. The monsoon is perhaps the most distinguishing feature of our climate in this region. Large parts of the region experience in that summer period, June, July, August, September, about 50%, about half of their annual rainfall. Okay, there are exceptions. So, and this gets at part of the question. Eastern New Mexico has low winter rainfall and is much less bimodal than Western New Mexico and Arizona. Okay. That being said, across the entire region, there is a peak in rainfall in the summer months. Okay, so July and August, for the most part, is when you experience your high rainfall. Now, there's exceptions to that, but we're talking on average. Okay, Western New Mexico and all of Arizona also have a period of very low rainfall. On average, they occur in the months preceding the monsoon. Okay, so that's a little bit of the rainfall character. Okay, so the drivers of climate, it is largely a function of where the Southwest sits in relation to dominant atmospheric flow. Excuse me. So the Southwest is positioned between the mid-latitude. Think about the mid-latitude atmospheric circulation. So think of our westerlies and the subtropical circulation. So it's located between that. So the fact that we're there influences and changes in the positions of the westerlies and the subtropical flow affect our seasonal climate. So it is a dominant region why we experience quite a bit of variability. Okay. Generally, the dry and the warm character is a function of we're largely under a semi-permanent subtropical high pressure ridge. Okay, so that gives a reason for being warm and dry on average. Okay. So again, I talked about the seasonal variability as a function of where the Southwest is relative to the dominant atmospheric circulation patterns. Adding to this variability is the fact that we live in an area with mountains, complex topography, so that has an imprint, a spatial imprint of let's say rain and temperature. Obviously, as you go up in elevation, you're going to get more rain and it's going to be cooler temperatures. So topography is an important part as well. Also, our proximity to the Pacific Ocean, Gulf of California, and Gulf of Mexico also influences our seasonal rainfall. And then finally, among the patterns that happen at seasonal and multi-seasonal levels, among those, the most influential is ENSO, El Nino and Southern Oscillation, or the El Nino and the La Nina events. Okay. So, Mike, that's a lot there. Maybe that's too much, but the sort of foundation of our climate of the Southwest is in what I said. Do you have anything that you want to add to that?
Yeah, so I'll even kind of throw in there. Maybe I'll throw this question back to you. What do you think? Is Northeast New Mexico full monsoonal, or is it hybrid, or what is it? I have an idea.
It is, I would say it's out of the monsoon, the main monsoonal. Like I would say it's not monsoonal. I would say it's more influenced by the Great Plains type of climate, which you can explain what that means. Then it is influenced by the monsoon.
Yeah, I think that's right. It's this northeast New Mexico, all of eastern New Mexico is it's such an interesting transition from eastern New Mexico to western New Mexico. And so when you see a lot of monsoon studies, and they'll try to draw boxes around monsoon regions, and there's a broader North American monsoon region that is very inclusive and it grabs a lot of the sort of southwest, even parts of the west, north of the southwest, and then reaches down into Mexico. But when you really zoom in on the Southwest, we tend to keep Arizona and Western New Mexico as the core of the monsoon region. And then there's this kind of area around that that can get in the monsoon season sort of bursts of moisture that will kind of flow off and move into those regions. So specifically about Northeast New Mexico, very interesting area of weather. And I was pulling up some different figures and some data on that location. And I found this really interesting graphic from the Weather Service. And I remembered it seeing in a publication many years ago, actually, when I was back in school. And it's the number of thunderstorm days per year for the whole United States. And there's an interesting bullseye. There's two bullseyes in the whole continental US. One is in central Florida, over 100 days of thunderstorm activity a day, a year in central Florida. And then in eastern New Mexico, right over northeastern New Mexico, over 60 days of thunderstorm days per year. So it's really interesting in the broader Southwest in Arizona, New Mexico, Northeast New Mexico is a hot spot for thunderstorm activity. And the reason is you have an extended season of thunderstorm activity. And as Zack pointed out, when we look at the climate of the Southwest, in Arizona, we have this bimodal precipitation distribution where we get winter precipitation, very, very dry spring, and then a real hard edge to the monsoon starting in late June and July here in Arizona. And that's when we go from very dry air into all of a sudden a shift in the wind direction, which is indeed what a monsoon is. And we get this introduction of moisture. In Northeast New Mexico, you're actually already in pretty good flow of moisture in April and May. And so you get that Great Plains springtime moisture from the Great Plains low level jet, which is pulling up all that moisture from the Gulf of Mexico. And you've got things like dry line interactions. And so we've got that dry air that we're dealing with in the springtime that can move all the way across Mexico or New Mexico and then collide with that. That will fire up thunderstorms. You've got topographic features in Northeast New Mexico, mesas and parts of the Southern Rockies that can pull in the moisture from the east, pull it upslope, and drive that thunderstorm activity. And I was looking at some data in the region, and so it's interesting. The climatology of precipitation for Raton, New Mexico, has the lowest chance of precipitation on any day of the year is actually in January. So January 11th, you look at all the data for Raton, New Mexico, on average, there's a 5% of precipitation occurring on January 11th. So that's the lowest day of the year. You rise up to over 20% in May. So you got this slow climb into a wet season in the springtime. And then you peak at August 4th is your highest climatological chance of precipitation at 41%. And then you fall off kind of like the rest of us through August and by September, the end of September, you're now kind of back out of the monsoon season. So I would argue that you're just on the like, can we give them like an honorary monsoon uh, contribution or certification or something like that? You can in that August, you're going to get both monsoonal moisture that will, if it's a really robust monsoon and it's reaching all the way up into Albuquerque and New Mexico. It will certainly interact with you in Northeast New Mexico, but you also have the benefit of all that Great Plains moisture reaching in from the east. So it gives you that opportunity to get a much longer extended season. I would say honorary member of the
I
Monsoon
like that.
Club.
I like that. One um, one quick thought, and I hope you didn't say this because I'm frantically um, Googling to find the right paper here, but look for topography. But it does, topography plays an important role here in that sort of in central to central eastern New Mexico. I mean, you have the higher elevations that then slope down into the plains. That to me would, as the moisture is coming up from the south, southwest, like it's going to act as sort of a barrier over those mountains. So
That's
there's
correct. Yep.
okay.
Yep.
So there's
Yeah,
there's
that topographic slope, on the Front Range actually drives the dynamics that are the Great Plains low level jet. So that elevated heating and the broad slope across the whole Great Plains is actually, one of the mechanisms that draws that moisture up out of the Gulf of Mexico.
there you go. Okay, so we settled on honorary. So
Monsoon
maybe
member.
maybe the answer is somewhere in between, but tilting more toward sort of. I mean, I'm putting words in your mouth here. Are we tilting more towards the plain state weather as opposed
Yeah.
to? Okay, there you go.
Yeah, I don't want to cut anybody out. Like I'm in a kind of an inclusive guy. So, but it's not as monsoonal. I think the awesome thing is that it looks like you have a lot more frequent thunderstorm activity than the rest of the Southwest. So we can be a little jealous of that down here in Tucson.
All right, question two. This is from Sarah. There seemed to be an abundance of decape. Decape stands for downdraft convective available potential energy. There seemed to be an abundance of decape this season, which is perhaps, and by season she means the monsoon, which is perhaps related to all the strong winds and hail we had this monsoon. So what is decape? All right. This is a technical question. So I think to answer this, I'm going out on a limb here because I'm going to try to explain what CAPE is, what convective available potential energy is. And then I'll hand it to you, Mike, and you can take the question about what exactly is decape. Okay, so CAPE, convective available potential energy. It basically gets at the heart of the monsoon. And if you're asking this question, if you're ever asking the question, why does it rain on some days and not others? You're kind of asking about thermodynamics. And that's what convective available potential energy is really focusing on. Okay, so let's try to understand what CAPE is. Okay. I'm cracking my knuckles here because this is not easy. This is not easy to do. So in simple terms, CAPE is the degree. Correct me if I'm wrong here, Mike, or if you have a better way of saying this. But CAPE is the degree to which air can rise. Basically, it's buoyancy, and that's a measure of its buoyancy is a measure of the atmospheric stability or instability. Okay, and that's important. So good monsoon days often have high CAPE. Not the only ingredient in the monsoon, but it's a really helpful one because it's talking about atmospheric instability. How can air go from the surface upwards? Okay, so we can measure CAPE. We often measure CAPE by sending up these balloons called soundings through the atmosphere. They're done all over the U.S. a couple of times a day. They give you so much data on temperature and moisture levels through the profile of the atmosphere. And then you build what has to be the most complicated scientific figure ever assembled. And that's the
It's really
skew T
true.
plots. Skew T plots. For anybody that's interesting, just Google skew T and watch some YouTube videos. I mean, it is amazing how much information is there, but it really and it really synthesizes a lot of meteorological understanding. It's a really important diagram. Okay, so let me try to go a little bit deeper on Cape. So think of the atmosphere. As you go up in the atmosphere, your temperature cools and the atmosphere gets less dense. It cools roughly at a temperature gradient of at a rate of about 6.5 degrees Celsius per kilometer. Okay, so that's just a general sort of environmental lapse rate. When we think of Cape, we're largely thinking about it in the context of generating rainfall and, more importantly, severe storms. So it's really useful to think about our monsoon season. Okay, so at the near surface, an air mass has some moisture in it, and that we characterize that moisture by a temperature, a dew point temperature. So a dew point temperature is the temperature at which the moisture in that air condenses and can rain out. So it's at which point the moisture is fully saturated. Okay, so more moisture in that air, you end up having a higher dew point temperature. Okay. The dew point temperature is always, well, actually, I don't know if it's always. I hate saying always, but it's lower than the atmospheric temperature.
It is.
Oh,
That's correct.
yeah.
Yeah.
Couldn't be otherwise. I mean, you could get hypersaturated, right?
You get super saturation, but it doesn't last very long.
Okay,
Yeah.
yeah. Okay, so the dew point temperature is lower than the ambient air temperature. So for example, you could have a surface temperature of about 76 degrees Fahrenheit, and your dew point temperature would be, it could be anything, but it could, let's say 60. Okay, so it's going to be lower. Okay, so if you raise that air and you don't change the moisture content or temperature, it may become relatively warmer than the surrounding air, right? So think of that like a balloon rising up and its temperature crosses a line or crosses the temperature value up in the atmosphere, right? So that air is now warmer than the surrounding air, just like a hot air balloon. And that's when that parcel of air can just lift on its own. It doesn't need any sort of mechanisms. It's freely convective. I hope I'm getting this terminology right.
Sounds good.
Okay, so in summary, so CAPE is a measure of basically how much buoyancy there is to the air. So if you lift air up, will it cross that temperature, the ambient temperature line, and be freely convective? Okay, and you can have different degrees of CAPE. So again, more CAPE shows the potential for more convection. Okay, and it's a function of how much moisture is in the atmosphere near the surface. It's a function of the temperature profile in the atmosphere. And it's also a function of the temperature near surface. Generally speaking, that's CAPE. It's more complicated than that. But Mike.
That's good. That's good, Zach. I visualized it. I visualized the SKUT. The problem is that I've looked at SKUTs a lot. So it's easy for me to visualize. So yeah, and I think you may have said this at the beginning, but CAPE is an acronym and it stands for convective available potential energy. And it's calculated when you look at these SKUT diagrams, it's an areal calculation. So you're calculating using calculus to calculate the area of that. And it's a handy metric because one of the things that you can do is you can do this proof on it. And if you multiply the CAPE in a sounding by 2 and take the square root of it, you get the updraft speed of the parcel in meters per second. So you could rough this out like 500 joules per kilogram of CAPE, which is, decent. It's not particularly high. We would consider, 1,000 joules per kilogram for a really active day here in Tucson. 500 was often what we'd see. In the Great Plains, you'll see numbers as high as 2,000 or 3,000. Real thick atmosphere, lots of low level moisture, really good temperature profiles. If you take something like 500, multiply it by multiply it by two, take the square root, you get a number that's about 31 meters per second, and that in miles per hour is about 70 miles per hour. So you can think about that amount of convective available potential energy is an updraft speed of about 70 miles an hour, right? And so
I love those rules of
yeah,
thumb.
those are I think they're real handy. They're rough,
The
and that they're so
pilots look at this.
it's turbulence, right? I mean, that would be kind of turbulent. And that's why you don't fly commercial airliners through thunderstorms because that you can imagine, or if you've ever been on a plane where you've accelerated upward and accelerated downward, you're part of those buoyancy, those aspects. And just like you said, Zach, the buoyancy, I always try to think of the extreme examples to help kind of visualize it. So we play this game in our swimming pool in the summertime to try to push like a ball to the bottom of the pool. That's an extreme example of the ball has air inside of it, very, very low density. The water outside of it is very, very high density. And so that that buoyancy is contained in that difference between the parcel, the ball, and the outside. So it wants to race up when you let go of it to the top of the pool to achieve equilibrium in that density. Same thing is happening in the atmosphere. So okay, so you set us up with this cape. So there's rising air. Whatever goes up has to come down in our atmosphere, right? It's a closed system. So if there's rising air, there's got to be sinking air. So we can have extreme examples in the summertime, especially down here in the Southwest, where we can have these events where thunderstorms will collapse in on themselves and they'll be called microbursts, right? And we can have dry microbursts and wet microbursts. So one of the metrics that meteorologists will use when they're looking at these thermodynamic profiles, the SQT diagrams, is another metric called D cape. So there's cape and then there's D cape, and they're not equivalent. They can be in very different directions. D cape is called downdraft cape. So it's the available energy of the acceleration of a parcel of air coming out of a thunderstorm back to the surface of the earth. And so what can happen then is that instability or that buoyancy can reverse itself by becoming cold and wet air relative to the surrounding environment. And the degree to how much cold and wet air there is will govern how fast the parcel comes back to Earth. So it's not exactly, but it's the opposite kind of mechanism. So to calculate down cape, there's a little handy kind of rule of thumb that you'll do, and you're basically going to take, and I had this written down here, and I thought this was kind of handy, is you're going to look at the temperature of the expected downdraft parcel. So that's basically at the bottom of the cloud of the thunderstorm. The air is now reversing and it's now cooled off in the thunderstorm cloud and it's actually gained some moisture to it. And so at that cloud, that's going to start to give us an indication of it reversing direction. And we're now going to think about something called the wet bulb temperature. And so the wet bulb temperature is the lowest temperature that can be reached by the evaporation of water from a parcel. So when you have a wet parcel of air at the bottom of this cloud and it's coming back to Earth, if it's hot and dry below that cloud, we're going to now start to evaporate water out of it. And evaporating water takes energy, lowers the temperature. And so the wet bulb temperature is going to give us an indication of how cold can we get that parcel of air relative to the surrounding environment. So the down cape then is, or downdraft cape is going to be the surface temperature. So if it's very hot out at the surface, say still 100 degrees below that downdraft, and say our expected downdraft surface temperature, maybe we're gonna bring that air down to 70 degrees or 60 degrees. The difference between that temperature multiplied by the force of gravity, and then also the depth from the cloud to the surface gives us an indication of what that available potential energy is. So you can just kind of use in your mind if it's very hot at the surface, if that expected temperature of that descending air is very cold, and it's a real deep part of the cloud. If the cloud base is quite high, then it's going to have a lot of room to accelerate. And that's going to be our days where we get really, really strong dry microbursts.
Okay, let
And
me jump in
yeah, go
here.
ahead. Yeah, please
No, because
do.
that's I'm learning something here. Sort of my eyes glaze over at this part of the meteorology.
Yeah, I
But
know.
okay, so you get decape, you get high decape values when you have high base clouds, when those clouds actually have quite a bit of moisture still in them,
Hmm.
and when you have higher sort of mid-level and lower level temperatures, which evaporates that moisture and causes the air to fall. And of course, the distance increases the distance by which it can gain speed.
Yes.
Okay, so well, I don't want to if you have other.
No, that I mean, like that's the crux of it. And so then we can take that conceptually and think about what are the days that look like days, right? So that's what you were going to go with this, right? Do you want to lead
Yes.
us off?
Yeah, no, go. That's
Okay,
exactly.
so Sarah was pointing out this last summer, we seem to have had, and I think we had a couple of different events that were big decape days, and they were actually kind of known ahead of time that they could be decape days. So downdraft cape days. The tricky part about decape is that it's often there in the thunderstorm environment, especially in a weak monsoon pattern when the moisture is low. On those days, we typically don't end up having a lot of thunderstorm activity. So the risk is there, but the actual occurrence of the thunderstorms is low. This
Wait,
was,
I didn't get that. I didn't
yeah.
get.
So,
On
right.
the one hand, I'm thinking that there needs to be, given that decape is a function of moisture at the sort of cloud-based level, then there needs to be some moisture around.
Yeah. So I mean, remember this last summer where we were so marginal on moisture, but we would end up having it would get so hot at the surface. We'd have those really, remember we'd talk about inverted V's. Inverted V soundings, again, this is so hard to visualize a SKUT unless you're looking at it. An inverted V just means that there's a very, very low surface dew point and a very, very high surface temperature. And what ends up happening is you go up in the atmosphere, there are some, physical lapse rates that these two variables, dew point and surface temperature, change with height, and they meet each other at the base of a cloud as through the convective process. And so even with marginal moisture, if it's hot enough and you can convectively lift that through a real deep mixed layer, you can actually still get a cloud to form. And if it's got a good source of moisture, it's like it's the cloud is the solar radiation is really good and the moisture is still available, we can pump up a thunderstorm. And even at very low dew points, you can get a thunderstorm to take off and still turn into an actual rain event. And if do you remember that this last summer, Zach? It was we'd end up having really, really like the dew point would suggest you're not going to have any thunderstorm activity, but it got so hot that it still sparked off thunderstorms across the metro area. They didn't produce a lot of rain. They produced a lot of wind, great lightning. They kind of, ran around the metro area. And on July 20th, the daily average dew point on July 20th was 52.5 degrees. I just looked that up. That was also the day that we had that huge straight line wind event from a dry microburst up in the foothills and on the northwest side of town. So that then suggested that that was one of those events where the thunderstorm got itself going, rose up, into a nice cumulonimbus cloud, and then as it started to rain out, it rained into that really, really deep cloud base, really, really big difference in surface temperature and dew point, and lots of wet bulb temperature potential, meaning that that there was a real strong potential that you could lower the cloud base temperature through that falling parcel and it accelerated to the ground. And so the decape becomes quite a bit lower as the monsoon gets more and more moist. Like if we have a 70-degree dew point day here, lots of moisture, we can have those really, really heavy rainers, but they're typically not going to produce a lot of wind unless you have really, really heavy rain that's a wet microburst. And that's just through the mechanical mechanism of tons of rain falling to the surface and just dragging a lot of air with it. But the dry microburst is really about the reverse buoyancy, heavy heavy wet air at the cloud base falling into a dry atmosphere, becoming even heavier because it's been evaporatively cooled.
So, okay, so getting to part of this question, in a dry monsoon, do we tend to have more days with higher decape, principally because the sort of the mid levels of the atmosphere are drier, so you
Yeah,
evaporate that whatever moisture is there and cause that acceleration and sinking.
yeah, it's that knife edge of it's the low levels of the atmosphere, it's the subcloud properties which are going to give you an indication of whether or not you're going to have that particular issue, right? And so it's it's that knife edge of is there enough moisture to even sustain or start a thunderstorm versus because if you can get it going in that environment, then you're going to have the potential to have a lot of downcape and have those wind events. But it's also on the edge too, where it might not be enough to actually get a thunderstorm going, and so the risk is kind of ameliorated.
Okay, so you need to have a thunderstorm, right?
You do
You
have to have a thunderstorm. Yeah, you can't do this without evaporative cooling.
Okay. So right. So it's those interesting scenarios where it's not a huge thunderstorm, right? Because then you well, I don't know, maybe I'm wrong on this, but it's not a big, powerful storm, but it's also so it's a small or clearly I'm not articulating this very well.
No,
It's
no,
not
I totally
big
get. I get what
as
you.
how you
Yeah,
were
it's
saying, but
yeah. We have those ones that are just like the wimpy storms on those hot, dry days that will, they're the ones that they never quite get going and then they become shaggy and they fall apart on themselves. There's wind every time you see Virga, you're going to have some wind associated with that, right? It's the really good down cape, decape days, downdraft cape days are when it's a real honest to goodness mature thunderstorm, like good big flat base, good convective tower, looks like it's actually going to produce some rain. And when it does produce that rain, because it's actually condensed all that water, even if it was not a lot of surface moisture to deal with, it was cold enough at the upper altitudes to actually condense that water and turn it into precipitation. Then you're going to have an issue. Mature thunderstorm with a high cloud base raining into a very dry subcloud environment. It's going to be wind. It's going to be totally going to be wind.
I see. That's cool. So, final part to this was this year, I guess we kind of already answered this, but was this year abnormally that it experienced more decape than otherwise? I think we already answered that, correct? Like it
Yeah,
did.
I think so. Yeah, I was just looking at the daily dew point tracker, and it was a really weird summer. It was not particularly well. We just came in just below average here at
For the
Tucson.
airport, but like not.
Yeah, for the airport, but across town it was a real mixed bag, and it wasn't as bad as was 2020. I think that was our refrain. That's what I got put on a t-shirt for this last monsoon. But we had several breaks in the monsoon where the dew point just kind of it slacked off, and those are the days if there is moisture hanging around and it gets hot, and we had all that heat too. The heat is also this part too, because if it's a cloudy day and the dew point's low or there's just not a lot of solar radiation, you're never going to generate enough cape to get a thunderstorm going in that situation. So you're not going to have to worry about decape.
Well, that was a deep dive on decape.
Yeah, we've never done a deep dive on decape. Yeah, we're gonna
All
have to
right, all right.
get
Let's move
SKU
along.
t-shirts made now
Yes.
too. The whole product line of Southwest Climate Podcast.
All right. Question three. It seems that an albedo effect after a good snowpack tends to influence the monsoon to some degree through delayed surface heating. Does this hold any water? So let me say that again. So first of all, albedo is a technical term that means just reflectivity. So high albedos are reflecting a lot of light. So whiter colors, lighter colors. Okay. So it seems that albedo affects, sorry, it seems that an albedo effect after a good snowpack season tends to cause a poor monsoon through delayed surface heating. Does this hold any water? All right. So this is from Mark. All right. So I'm remembering, Mike, that this was a pretty hot topic. Thinking about the snowpack's influence on the monsoon season was a pretty hot topic, decade ago or so, or even before that. But I went around and I dug up a few more recent papers. So I think there's a couple ways to look at this question. There's the question of reflectivity, right? And then there's the question of soil moisture, which snowpack influences soil moisture. And so both of those things can be at play. Like higher reflectivity, like more snowpack, would basically limit the amount of energy that is available to go into surface heating. Okay. Now more snowpack would also increase soil moisture, which also affects how the energy that's available gets partitioned. So you either put energy from the sun into evaporating melting the snowpack and evaporating the moisture, and that's called latent heat, or you put it into warming an object. That's called sensible heat. Okay. So I drew from a paper, which I'll give the reference in a minute, that I'll summarize it in this way. It was nice from 2021. It was nice in the sense that it provided mechanisms for how snowpack can influence the monsoon. So what they state in the paper is wet soils in the southern Rocky Mountains. So this is a region in this paper that is basically the higher elevations of Arizona and New Mexico northward into most of Colorado and Utah. So wet soils in this region result in lower than normal local surface temperature, weaker water vapor transport from the Eastern Pacific and Gulf of California, and less monsoon rainfall. Okay, so let me explain the mechanisms here that they cite. Okay, so bigger snowpack, higher soil moisture. Okay, that means that there is less sensible heating of that region because the energy available is going into melting the snow and evaporating the moisture, and not into warming the land. So you end up having lower surface temperature. That lower surface temperature has an influence on the atmospheric circulation, which we can talk about in a minute. What that does is it reduces the water vapor influx, the moisture influx from the Eastern Pacific into the monsoon region. And consequently, we have lower monsoon rainfall. So, Mike, how robust is that kind of mechanism? Before you answer that question, let me say that you would think then, given what I just explained, that there would be a high correlation between high snowpack years and monsoon rainfall. Correlation between snowpack and rainfall. Turns out the correlation isn't that high. And that is and I think this is an important point of this story. There's many ways to influence monsoon precipitation, right? This mechanism that I just described is one of those ways. So you actually, if the monsoon was simple and it was only driven by, snowpack conditions in the high country, if that was the only reason, you would expect there to be a high correlation between, and a negative correlation at that, between snowpack and monsoon rainfall. But because there's other mechanisms and the monsoon is a very complicated process, like you actually end up having a low correlation. So I think that's an important point that there isn't any one single driver of creating a good or a bad monsoon, but there seems to be a mechanism here that can link greater snowpack and consequently the partitioning of the energy available to monsoon conditions in the Southwest. Mike, talk to me.
Yeah, yeah. No, I've really struggled with this because this has been something that we've wrestled with for the whole time we've been here in the Southwest trying to understand this. The literature, as you pointed out, it's kind of all over the place on this, and the correlations are weak. So conceptually, the way you just described that, based on that recent paper, and there's a couple other that are kind of that lineage, it makes sense, and there's probably something there, but it still seems to be only a minor component to try to explain any kind of interannual variability or variability year to year. And so I guess what we're saying, when there's a low correlation, what does that mean? It means that there are plenty of years where we end up having above average snowpack or above average soil moisture in the Southwest, and it's followed by a just peachy fine total seasonal total monsoon precipitation, right? So that would suggest then, and that's why you get the correlations that are low. And I think it has to do with what you just said, that to get to the seasonal total, there's so much that goes into that. It's where it's raining, when it's raining, and those kinds of things. I think from first principles, and this is where I think people are kind of honing in on, is that mechanism probably makes the most sense at the beginning of the season with the onset, right? Is that it should signal a slow onset. The thing that I always get hung up on, what you just said, is that there are so many moving parts, and we know that it's weak. Again, it's weak too. We know there's an El Nino La Nina part of interannual variability with the monsoon, even though it's again quite weak. And often what you can have happen is that you can have an above average winter precipitation total for the Southwest governed by the phases of El Nino and La Nina. And whatever that bigger atmospheric forcing is with ENSO, it can linger into the spring, and that can actually influence the onset of the monsoon rather than the local forcing of the changes in the local soil moisture. And so it's like it's an attribution problem, and we've never been able to kind of parse out in piecemeal the different components of the attribution. But I think the work is still going there. It's because we don't model the monsoon circulation very well. So it's even hard to just replicate it under a controlled situation without actually changing all these other levers and dials on the monsoon.
I mean, some of the other critiques I think that I've heard along the way is, I mean, the monsoon has as a principal driver, a regional feature, the position of the subtropical high. And this idea of the soil moisture feedback is a regional signal that is running up against
Yeah.
The larger sort of circulation pattern. And so the influence of it is probably or likely a lot less. Doesn't mean that there's not some information to draw from that. And I think that's what this paper is getting out. But if you're thinking about, well, what's the biggest piece of the pie? Probably the consensus is that the sort of land surface feedback from snowpack conditions is probably not like you couldn't build a predictive model, a very useful predictive model just by looking at this particular uh, condition.
Yeah, and we've tried, and this is the this is the kind of sticky thing with a lot of the statistical models is that sometimes that correlation is right for the wrong reason, and this is where the attribution I think is really important, and it's really hard to do. Is that local forcing due to snowpack or lack of snowpack? Is it big or small? It's probably small, but is it more important in certain years when other things are going on, like phases of El Nino or La Nina? And we don't have a lot of good contingencies in the historical record to actually tease that apart. So it really does become a modeling exercise, and then modeling the monsoon with land surface feedbacks at very small scales is hard to do because you've actually got to get it right all the way down into like Central America, all the way up through North America. You've got to get all the small things right to actually pick apart the pieces of the local forcings.
So we'll post the papers that we reference here in the show notes. I'll just read the title of it. It was published in Journal of Climate in 2021. It's called Observed Influences of Soil Moisture on the North American Monsoon, an assessment using a stepwise generalized equilibrium feedback assessment method. I have to say that, when I was researching this, it's not a literature that I am all that familiar with, or at least the recent stuff. So I just picked this one out. There could be other ones, better ones. I picked this one out because it had a really nice, elegant conceptual model in one of its figures. Basically, I read that to you.
Yeah, yeah.
So I think it's helpful in that sense. But we'll
Yeah, no,
post.
I think it was a good paper, and I think it's onto something. It's just that I still don't think it's a particularly powerful rule of thumb for us because we don't quite understand it, and the correlations are quite low.
Okay. All right. Moving along. Couple really fun questions.
Hey, Zach, can I jump in real quick?
You can.
I have to do real-time error checking and fact checking on myself here.
Okay. Okay.
I just wanted to point out when I was talking about the wind event in Tucson, I was off by a couple days, and very astute listeners, it was actually July 18th that
Oh,
wind event was. I had picked up the wrong event. This is in July 18th here in Tucson. I was talking about with the D Cape, and the dew point. The dew point was a little bit higher. It was still kind of a marginal day, but I didn't want people scratching their heads going, "Wait a minute, it didn't rain on July 20th," because I don't think it rained on July 20th.
you're multitasking. I'm impressed.
I am. I'm trying to do it all at once.
All right. Well, thanks for that. Okay. Um, that goes to your credibility, Mike. So it's good that you clarified that. All right. So the fourth question. I'm wondering whether there's a clear global warming signal in the monsoon. Another question from Sarah. Don't know if this is the same Sarah, but a fantastic question. So I'm wondering whether if there's a clear signal, global warming signal in the monsoon. All right. Okay, so a couple ways we can look at this. Let's take observations first, Mike. So
Okay.
this is a particularly hard question to answer by looking at the observations. And we've talked about this a lot. And the reason is the monsoon has a lot of spatial and temporal variability. And when you have systems of high variability, it's harder statistically to generate a signal from that noise. So you end up needing a long record, and that's not something that we have long enough here in the Southwest. But the spatial component of this, you have high spatial variability, also means you need to have high spatial coverage. And we just don't have a long enough record to understand some of the trends. There's a caveat to this. In my mind, there is a clear warming signal in the monsoon. It's getting hotter, right? And I think that is because the spatial variability and the trend in warming is much stronger than it is for any trends spatial or temporal in rainfall. Okay, so you can you can add color to that if you want about the temperature part, but let's put the temperature aside because when we think about the monsoon, most people are thinking about rainfall. But
Yeah.
I just want to stress that there is a temperature signal and you can see it, and it aligns with what we would expect, and it's pretty robust. Okay, precipitation. All right, so I think the simple answer is that a couple things that we maybe would expect from a warming climate is an increase in the intensity of rain. And the expectation there is because in a warming world, right, we know it's getting warmer, that the atmosphere can just hold more moisture. And so when it does rain, one might expect the intensity uh, to be higher. The other part of this is the frequency. And that is maybe, I'm not sure that there's a clear theoretical reason for in a warming world why there would be increases in the number of rain days. But I think that there is a clear expectation for more intense rainfall. And this is sort of behind the idea of extremes are increasing in a warming world. Okay, so first of all, anything do you want to add to what I said, Mike? No, okay, right. So looking again at the observational record, there is an interesting paper by Eleonora Damaria published in Geophysical Research Letters in 2019 called The Intensification of the North American Monsoon Rainfall as Observed from a Long-Term High-Density Gauge Network. Okay, so they looked at a small part of the Southwest where there is a high density of rain gauges, 59 of them, southeastern Arizona. And they looked at the sub-daily and daily changes in rainfall. So kind of getting at this intensity question. Okay, and so what they find is that there has been an intensification of the monsoon sub-daily rainfall intensities starting in the mid 1970s that has not been observed in previous studies or simulated with high resolution climate models. So they, looking at the observational record in this smaller area, they conclude that there has been an intensification of the sub-daily rainfall. I would say that maybe that's a little, I don't want to critique the paper, but I will say that when you look at the data that they plot for different sub-daily timescales, like a half an hour and a half, 4 hours, 1 hour, 2 hours is what they look at, and the full day, 24 hours. Like there is a change in the intensity at those different timescales, statistical change, but like when you just zero in on the later 30 years of the record, so like there isn't much of a change, so it's almost like so I'm looking at the figure now and it's like from like 1980 to the end of the record, I think it's like 2000 and let's say 2015 or something like that. Like there isn't much of a trend there. When you extend the record back to, 1950, you can pick up that longer trend. I don't know, Mike, are you looking at this paper or not?
Not this particular one right now, but this one. But
Yeah.
I have some recollection of it a little bit. Yeah.
Yeah. So I think, yeah, I think if I'm reading this correctly, that a lot of the trend comes from the extended record, but then when you zero in maybe on the last 20 or 30 years, there isn't so much of a trend. And so the question that I would have, I'm not disputing I'll let people read the paper themselves, because they do conclude that they found an intensification. I'm not disputing that, but I do wonder I guess the question that I would have is like, why don't you see it in the last 30 years? Why don't we see a continuation of that intensification? I mean, maybe there is an explanation for that, but I don't recall them addressing that. I don't know if you have any thoughts on.
Yeah, I mean, I think this is the real challenge with the monsoon. You laid this out at the beginning, is that our monitoring networks aren't up to the task, quite honestly, of being able to track this change. We don't have the right kind of monitoring at the spatial scales and temporal scales to do it. So the real strength of that Walnut Gulch study is that I think it's the only place in the world that has that density of rain gauges that's sub-daily and even, down to hourly precipitation. So it's the only place you'd be able to detect anything like that. And also, I think that, even if the trend isn't, perfectly linear and kind of extends to the end of the record, I mean, it does show a change from the early part to the later part of the record. And that is consistent with a warming climate. So I think that we do have, I think that that's probably the most refined evidence that there is a hydrologic or hydrometeorological change occurring in the monsoon. And that's consistent with what we'd expect with increasing amounts of moisture in the atmosphere. The climate models have suggested now for the last couple of iterations, CMIP runs, the IPCC level, which again don't they struggle a lot with resolving the monsoon. But one of the things that is been observed in modeling runs in dryland areas with monsoonal climates into the future is an increase in precipitation intensity, but a reduction in the frequency of rain days. And so there's like that study starts to show the intensity change. The other things like we can't really see intensity really from our daily observations, which is most of the rest of our network. And all of our gridded data is from daily observations. And, we've got thunderstorms occurring between gauges. So the frequency of precipitation days and totals is a struggle to see any trend or change in it over time.
Yeah, so this is a really cool study. People should read it. Eleonora Damaria, we'll post it in there. I just to put a bow on this particular study, there is some evidence of an intensification at the daily levels. Like Mike said, this is one of the few studies that has a data set, spatial and temporal, that can resolve it. So there's something there.
Yeah, they argue in that paper that we're not up to the task of actually doing this, at larger scales because of our monitoring networks.
Okay, so you sort of alluded to this. The second way that we can get at this is, what do the climate models say? What are our state-of-the-art modeling for the monsoon tell us about the monsoon in a warming world? Okay, and so this is a vast literature. I went down a wormhole. I think the upshot is we don't know. Okay. It's kind of all over the place. I'm going to juxtapose this with four different studies here. Okay. So we'll post these again. We've got a Nature Climate Change paper in 2017. Well, let me step back. So the reason why we don't know for climate change, looking at the climate change signal in the monsoon, is because our tools aren't yet good enough. And the reason for that is they have coarse resolution. There's ways to get around that. There's smaller models that can actually resolve sort of convective kinds of processes. But generally speaking, there's coarse horizontal resolution. There's systematic sea surface temperatures biases in these models, and combine those sort of limit our numerical model simulations. There's other knowledge gaps, like just our ability to simulate the effect of ENSO on the monsoon. And again, this is sort of a complicated, what you said before, Mike, we've got to get it all right, over a huge area. And so it's an incredibly difficult problem to ask of the current tools that the modeling tools that we have to ask it. That doesn't mean we don't try, and that doesn't mean we can't understand things from the modeling process. It just means that we're likely not to have a very definitive picture at the moment. And that is, in fact, what we have. So this 2017 Nature Climate Change paper states once the paper sort of tries to minimize that sea surface temperature bias, the paper states, the model projects a robust reduction in the monsoon precipitation over the southwestern United States. And the reason for this is that it can be attributed to increase in atmospheric stability. So we talked about this before, and hence weakening convection. Okay, so the Nature Climate Change paper is calling for a robust reduction. Another paper from Geophysical Research Letter published in 2022, the title is Increasing Future Precipitation in the Southwest U.S. in its summer and its contrasting mechanisms with decreasing precipitation in the spring. So that's the title. You get the upshot from the title. So it's projecting an increase in future precipitation. Okay, so a third paper calls for, the title of this is The North American Monsoon Precipitation Response to Climate Warming at Convection Permitting Scales. So this is a paper that tries to use smaller resolution models so that they can get at the processes that are driving rainfall in the summer, which is convection. And they call for an average increase in portions of Arizona and New Mexico during the June-September period, so during the monsoon period. And I think you alluded to this. What's interesting here is it is that there's a decrease in frequency, but an increase in intensity. And that's what's driving the total increases.
Right.
Okay. And then finally, adding to this complexity, another paper, future land precipitation changes over the North American monsoon region using CMIP-5 and CMIP-6 simulations. This was published in Journal of Geophysical Research in 2022. What it found is that minimal changes overall. So the total isn't showing much of a sign, but there's reductions in the June through August period of the season that are offset by increases in the September-October part. So getting into a little bit of the tropical hurricane remnant influence. But so you've got differences in the sign, increasing versus decreasing, changes in, the sort of when the rainfall is happening. Some say it's happening more in the beginning, or sort of less in the beginning and more at the end. And spatially changing the character intensity versus frequency is changing. So all of that is painting a very challenging, incoherent picture of what the monsoon is going to do in a warming world. So I think the bottom line for the climate change studies is very important question. It is active. There's a lot of people going after this. The tools are getting better by the month, if you will. The analyses, the methods are getting better, but it's still unclear what's going to happen in a future warming world. Mike.
Yeah, I'll just add on, Zach, that it's just what you just said is that what's changing about the modeling is the convective permitting modeling efforts that are underway now. So the previous the Pascal paper that you talked about from Nature in 2017, it was a really interesting paper in pointing out that the bias in the global models is problematic with looking at the monsoon, but that paper only used one global climate model to make that sort of assessment, right? And so we don't do that very often in using GCMs. We often use ensembles because we're concerned about the performance of one model relative to having the uncertainty in that particular model relative to the other ones, right? So it's still this real challenge of taking all of this modeling work that is not at the scale of growing thunderstorms. That's what convective permitting means, is that you've actually, those models don't grow thunderstorms. You're trying to infer where the thunderstorm activity might be in big, giant, you know, grid cells. And so since the monsoon is a lot of fine scale processes, I think that's often why we miss out on any kind of certainty when we do these projections going forward. That one paper that you're talking about with the convective permitting scales was really interesting because it gets into the nuances of Gulf surge days versus non-Gulf surge days. So you know you're not going to see Gulf surges in a global climate model. So you've got to come down to the level of the North American monsoon to see the subtle, you know, interdaily kind of events like a Gulf surge versus not. And you know what they get out of that is that just what you said, Zach, is the increase in precipitation overall is due to changes in Gulf surge frequencies, more moisture in the atmosphere, more convergence of that moisture, and heavier rain events. Maybe not a change in frequency, but a change in intensity over time. I will say that that Demaria paper, we should give props to Chris Castro and his lab over the last 5-10 years. They've written a couple papers too that have hinted that you can kind of see a change in intensity with some of the daily networks, but they also recognize that the observing networks are not really up to snuff to see some of the subtle changes that we would expect to see in the modeling projections.
I mean, what do you think if you had to make a bet on the future monsoon? Will it intensify? Will it decrease in intensity? Like, will it look largely the same as it's been for the last 20 years?
I think the changes will be subtle, and I think that what we will see is heavier rain events within a largely familiar monsoon pattern going forward. The thing that, geez, how many, Zach, we've been doing this podcast for over a decade. How many of those 10 or 12 monsoons that we've talked about have looked similar to the other monsoon that we've talked about,
None of them.
right? Like I know they're so different. It's like 12 different flavors of ice cream. And again, it's not to say that there's wildly different physics going on in every one, but just the way they evolve, where it rains, when it rains, how much it rains, that to me is there's so much noise in this, you know, over time. I expect that that's probably going to continue, and we'll see more surprise events like, oh my gosh, it rained 5 inches instead of three, and we might have longer breaks between a 5 inch event. You know, it's that I think the changes will be subtle in a hotter climate as well.
Yeah, I think that's a really good point. Like the point that we have to look at we have to be a little bit of a detective here and look at
Yeah,
the the characteristics of the monsoon and try to detect changes within those. It could be breaks, it could be surges, intensity. Like there's maybe a spatial component of this too. Like maybe the core region like changes a little bit, and so there's a
yeah,
whole bunch of nuances I think that we'd want to look at if we had the ability, at least in the observational record.
right.
You
We
know, and
we
like
even we even have a paper we're working on, right? Where
probably
where
won't
we're
see the
trying. Yeah.
probably won't see the changes in the totals or
Yeah.
the level of variability or those kinds of things, but maybe we'll see some changes in other things. Yeah.
That's right. And I think that often the studies are on seasonal totals, right? And so then we see poor correlations. But you're right. The detective work is probably in the forensics of, oh no, stuff is changing, but it's changing in these subtle ways. Or it's or there's such little similarity from year to year that overall the it's going to be really hard. Like the signal to the noise is that ratio is going to be low, and it may always be low because of the nature of the
So this
monsoon.
is a similar question. Okay, this is from Bruce and Joanna. We're wondering if anyone is studying whether climate change could eliminate the North American monsoon as we know it and leave Arizona high and dry. All right, so I love this question. So what would it take to shut down the monsoon? So first of all, the question is about, is anybody studying it? Like I a lot of people are maybe asking the question about what's going to happen to the monsoon in a warming world. I don't know of anyone that's done experiments about like, well, how do we shut down the monsoon? But I think that's a fantastic question, right? So let
Right.
me let me let me throw out a couple ways to get at this. One way is let's take recognizing what we just said, which is the climate model tools are imperfect, but they're what we have right now and they're useful.
Right.
Let's give it a really hard thump in terms of a a future warming projection. So let's get a high end scenario and see if we can break the monsoon. And so a paper actually did this. I don't think it was asking the question that we are right here. I mean, it was just trying to understand what would happen to the monsoon using what's called a shared socioeconomic pathway scenario 5. So the climate modeling community has a number of different visions of the future that go into go into how they're describing the greenhouse gas concentration, for example, in the atmosphere. It's a little bit more complicated than that. And and so it's a way of understanding, what will happen in a future climate, like when we hit it with high levels of greenhouse gases, if you will. So, and there's different scenarios that they're using. So this one uses a shared socioeconomic pathway 5, which is a high development, fossil fuel dependent future, and using a radiation forcing scenario of 8.5. All you need to know is that's the hell on fire scenario, if you will. That's like one of the more extreme scenarios for future climate change. Really handy to sort of ask questions about this kinds of thing, the sensitivity of our climate to the climate forcing. It's not a scenario where many people think we're actually going, thankfully. 10 years ago, I think this scenario was more in play, but the way that the world is moving is much further away from this kind of a future than before. But nonetheless, like a good hard thump to our atmosphere. So you can't, under this scenario, you're not breaking the monsoon. The monsoon is still there. It's still present there. In fact, let me see if I can't. So what it says is it doesn't shut down the monsoon. It produces minimal changes in total land rainfall. Again, this is actually, we referenced this before. This is the paper that minimal changes. What you see is a reduction in frequency, but an increase in intensity, but monsoon's still there. So not breaking it through a warming world, a vastly warmer world. Conversely, I sort of looked at, well, what's the opposite of this? What did the monsoon, what was the monsoon like 20,000 years ago when we were at the height of our last glacial maximum? So when we had like big ice sheets draping over the northern hemisphere, the Laurentide ice sheet, like was the monsoon still present there? So these would be like kind of two extremes. And this was actually work done by our own Jessica Tierney in the geoscience department, second author on it, paper in Geophysical Research Letters from 2027. And the upshot of this is the monsoon weakens slightly, but it's still there. So even during the time in the last 20,000 years when the world was coldest, seven. I used to know this because I used to study this. I'm trying to think
You're
about
the paleo guy.
what the global temperature was like at 20,000 years ago.
It was colder, right?
It was much colder, 5 to 7 degrees Celsius colder, I think.
I got the
Anyway,
direction right.
it's much colder. Monsoon's still there. So I I think the monsoon character changes, but doesn't, but the monsoon doesn't go away. So I don't think we can break the monsoon, at least not under current plausible futures.
Right. Yep. Yeah, I
Anything that,
totally agree. Yeah, I mean, I may have dreamed this, and I may have like hallucinated this like artificial intelligence would be, like ChatGPT, but I thought I read a paper where they did some sensitivity analysis on changing the topography of the Southwest. And I was telling you this, Zach, that I thought I read somewhere in one of these papers that if you remove the Gulf of California or remove the southern Rocky Mountains and the Mogollon Rim, then you do shut down the monsoon circulation here in the Southwest. So it's the interplay between the higher elevation, elevated heating of the Colorado Plateau and the Southern Rockies and the Mogollon Rim, and the long desert coastal plain that reaches into the northern Gulf of California. It's that interplay of access to moisture and elevated heating that drives a lot of the precipitation in, at least in the Arizona part of it, of the North American monsoon.
that's really cool. See, this is where I think the modeling studies and these more extreme scenarios like really have a use. You
Dude, that's what
can do
models are.
these experiments. Yeah,
Yeah,
you can do these experiments to learn
yeah,
about how, the sensitivity of the climate, like what is its principal drivers, right? Like let's remove the Gulf of California and see what happens to the monsoon, and that gives
yep.
us some insight into the importance of the Gulf of California. So
Yeah, that's fundamentally the utility of models is to do case study sensitivity analyses and experiments. It's where we've tried to make them predict the future. That's
yeah.
been the tricky part.
All right, finally, Mike, um, we'll end with a really fun one. Okay, so this is from Neil. Like many people in Tucson, I'm engaged in a lot of outdoor activities, and during monsoon, these activities get pushed further up the mountains for temperature reasons. One thing that is always complicating factor is trying to read the weather pattern and determine whether we're going to get dumped on or caught in a storm. Some clouds pass right by without a peep, and others seem to become a problem very suddenly. Are there any tips you can share on how to read different monsoon clouds? So I'm going to throw this to you.
Oh, this is interesting. He threw a little curveball in there that I just realized that he put in there. Is that he's trying to read, I think he's trying to read the clouds when he's up in the mountains. And that is a lot harder. Okay, so I'll tell you as a valley, desert bottom dweller, what I look for during the monsoon season. And you and I chat about this. We're texting each other constantly during thunderstorms. Is what I've realized living out here is that the storms that end up becoming dumpers, it has a lot to do with the time of day, given the sun angle and the position. But if you get a nice flat cloud base below a thunderstorm and it starts to get really dark. This is kind of super obvious, but it really does hang true because what it's telling you is a cloud that has that morphology, a real nice flat base to it, and it's quite dark underneath it, means that it is in the updraft stage of the storm. So it's there's air rising into it, so it's in its maturing stage, and it's really thick because it's casting a really dark shadow to the bottom of the cloud base. If the sun is high, that sunlight's not getting to the bottom of it. Those are the ones that you got to watch out for because they're going to reverse from the updraft phase into the downdraft phase. It's the clouds that have always disappointed me are the ones that the base is kind of shaggy and it's already got some virga. You already know that that one's probably not going to be promising and it's probably not going to do anything for you. The trick is when you're up in the mountains, it's hard to see the cloud base because often the cloud base will intersect you, and so it's difficult. The thing about mountains in the monsoon, you're probably going to get rain. Like that there's such a better chance of even a lame kind of bit of convection and cloud turning into some kind of precipitation because you're driving the convection while you're in the mountain, and those clouds aren't going to have the same kind of morphology because they're interacting with that topography. So that's
Let
probably
me
the
add one.
best tips I can get you. Yeah.
Yeah. What about, and maybe this isn't like, I mean, I guess you could see it in the mountains, but what about those scenarios where you end up having like really high wispy clouds that sort of shade, like they're basically the tops of these anvils that end up shutting down the 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 generation of this storm. So it, anything there. So what that would look like is you might see like off in the distance if you have a view like a big looking cloud, but the tops of it, if the tops of it, if the wind is blowing the top in the same direction that the wind is blowing the base, like that top of that anvil ends up shading below it and shuts off the convection. So anything there, Mike?
Yeah, it's that is much more an issue in the valley,
Yeah.
right? And it's so much easier to make it rain up in the mountains, even with poor conditions, right? Time of day can be helpful in sort of reading the clouds. So, if it's 10 in the morning and it's on its way to noon and you're starting to see cloud development, that's a pretty good chance that it's going to turn into some kind of precipitation regardless of the cloud type. If it's later in the day, sun angle's on its way down, so cloud development is going to most likely convectively start to be waning. So you can, but we all know that, right? If you're hiking, everybody tries to leave before sunrise and be up and down before early afternoon because that's always when, you're going to have peak thunderstorm activity is, just afternoon.
So do you know offhand, like if you look at like the Tucson airport, on average, over the course of the 100 days of like what we define the monsoon season, it rains 25 days. So it's like every 4 days it'll rain. Like on top of Mount Lemmon or on the mountains, is it like every 2 days? Like, do you know those stats offhand?
Yeah, I think we look at that. I had a climatology of frequency of precipitation. It's 2 to 3 times more
Yeah.
than
But
than
in terms of
Tucson, the
total
airport.
amount, but what about frequency?
Frequency too. Yeah, because it roughly scales. As frequency goes up, the totals are going to go up. So yeah, like the high country of Arizona, in a good monsoon, we'll see 50 to 70% of the 100 and what is it, 128 days of the monsoon will
I think it's
see
100.
rainfall. 100 days. Yeah. So yeah, so that that's more than half to almost two-thirds or over two-thirds of the days are going to see that level of precipitation.
So that's one
So
way.
it's
I mean,
almost
just
like climate.
expect it, right?
Yeah, I'm just
Like
like you're
expecting
right.
it to see clouds and
Yeah.
it's probably going to rain. I guess the question is like, is it like a super intense thunderstorm with a bunch of lightning that can be dangerous, like, or is it a little piddly, wimpy storm? I
Yeah,
guess that's a hard thing. Yeah.
it is our thing, and I think that what you can anticipate is often, the dew we you and I talk about dew point, right? So if it's a as the dew point creeps up and you're heading up in the mountains, you're going to have a better chance of maybe earlier precip, more precip, and possibly more severe. If it's a dry day, it's going to be even tougher. It'll be tough up on the mountains to generate heavy rain. It'll still probably rain, but yeah, it's funny we're trying to give them weather tips, and I reverted to climatology saying just expect it to rain.
Yeah, that's good. Okay. That was fantastic. Really appreciate people for sending us those questions. This was a lot of fun for me. Um,
Yeah,
and it's great that we have some listeners who enjoy us chatting about the weather because we love to do it. So, and the
we
climate.
do. Yeah,
Other
thanks for all that prep work, Zach, and yeah, thanks Stacy for the mailbag idea and coordinating that. And yeah, a lot of fun. Let's keep doing this.
All right. So have a great holiday, everyone, and looking forward to another year of the Southwest Climate Podcast.
Yep,
Saludos.
only 6 months to the monsoon or so, Zach.
Yeah, today was all monsoon. I mean, how about
It
that?
was, I know. We got to live it up.
All right. Thanks, Mike.
Thank you, Zach.